Okay, after seeing the evaluation code that performs the forward and the backward propagation, it's probably time to see how the training works. So in our scripts, in our network, we have been calling this method called CNN train DAG with a couple of options, like network, the IMDb, a function to retrieve the Minibatches. And now it's time to see how this function works. So this is not supposed to be a super sophisticated training function. This is just an example provided by MatConvNet guys. So you are free to modify it, and I really encourage you to modify it. So the first thing we see here are a couple of predefined options. So in case you don't assign any different values to these options, those are going to be the default values. You see that when we initialize our network, we are overriding some of these values. So for example, the batch size is set up to 100, number of epochs set to 20, and so on and so on. You see that here the predefined values are different. Okay, one of the things to notice here is that there is a parameters we haven't defined in our network, and therefore it's taking a predefined value, and this is the derivative output field. So before I was explaining how the backward propagation was working, like starting from the derivatives of any of your layers. So when we apply the chain rule, so when we do back propagation, at the end we have like a loss function that is a function that maps from Rn to R. So when we compute the derivative of that loss function according with respect to itself, so when we compute derivative of L with respect of L, we get like 1. That's actually this one here. So when we compute the end of the chain, we get a 1, and this is how we initialize the chain of derivatives to perform back propagation. We only have to select which layer is going to be the end of that chain. In this case, the objective, the layer called objective, or the output called objective, which is our loss function, cross entropy. Notice that we have left outside the error function, because this one we don't want to adjust it or to take it into account to perform the adjustment of the parameters of this network. This one is just supposed to be here to compute statistics, so it's not interfering with the training. Okay, you could change this and assign a different layer name, and that will be fine. So you can try it if you want. Then we have a function to extract some statistics. We will see that later. And this function here is parsing the parameters we have defined. So basically it's checking if these options actually exist, and in case they exist, they are gonna copy the values assigned by the user. Okay, because here we have some like optional parameters we can pass through, and through these optional parameters we are actually passing the option extractor. Okay, that is where we have defined our options. So long story short is that this parser takes like the predefined options and the option passed by the user, and for each of the possible options it checks if the user has defined something new, then it assigns it to the current variable. Otherwise it takes like the predefined value. That's it. Then the code basically create the experiment directory and form the training and the validation vectors, so basically containing the IDs or the IDs of each of the images belonging to the training set and the validation set. Okay, sometimes it takes like one for training and sometimes two for validation, but some other times it uses 3 for validation. So this is something you can change. So basically when you create your IMDb and you assign like which images are going to belong to training and which are going to belong to validation, you assign some indices, the ones you choose, and then here you can change that. In any case, have in mind that you also define we are also defining this here. Okay, so for us these variables are going to be overwritten, so this is not taking any, it is not producing any effect in our training right now with the current configuration, but otherwise it will be assuming that the default value for validation images is 2, so set equal 2. So now the initialization of the net. So the function get batch, the one we have defined and passed by parameter, is called in order to get a first batch and to check the sizes and so on. The network checks if we are in evaluation mode or not. If we are not in evaluation mode, that means we are in training mode, and some derivatives have to be assigned. So we need to start the backward propagation from any place. Then we have this piece of code which is on charge of initializing the GPUs in case we are using GPUs. So in case we have more than one GPU, it's calling a MATLAB functionality in the parallel toolbox that is going to do the multiprocessing stuff, and it's initializing like a number of pools, also called workers, as many as GPUs we have, and is initializing each of those GPUs. If we have one GPU, then it's just initializing that GPU, otherwise it doesn't do anything. Then this is just assigning some specific names to the partial models we are going to be storing and to the statistics in order to later save those files. We check if the continue option is activated and if there was already any partial models in the working directory, and if so, we load it. We load the statistics for that model, so the previous statistics and the net itself, because we are going to continue from where we left it last time. And now we go through the actual training. So for each of the epochs we define, and until the numbers of epochs we define, we are going to keep looping. So we take the current value of the epoch, so epoch number 3 or 4 or 5, we adjust the learning rates. So basically here you can see that the learning rate is taken per epoch, so you can define a different learning rate per epoch, and once we reach like the last learning rate, we just take that one, so the last one available. in case we have more epochs that learning rate defined in our learning rate vector. Then we take the indices of the training images and we shuffle them, so we perform a random permutation. So every time we start, we have a different permutation of the images. That's gonna be very helpful to avoid like cycles. If we have just one GPU, we call process epoch for training in training mode and process epoch in validation mode. Process epoch is the function on charge of doing everything, of doing the forward propagation, the backward propagation, and the optimization, so the adjustment of the parameters, in this case applying stochastic gradient descent. We will see that function now, but before that, let's finish understanding this piece of code. So this was the case for like one GPU or non-GPUs, and this is the case for multiple GPUs. For multiple GPUs, things are a bit more complicated because the different workers have to run this code in parallel in a sort of independent way. So what is going to happen here is that first the network, which is a DAGNN object, is going to be saved into a MATLAB structure. So save object basically gives you the equivalent MATLAB structure. This is due to the fact that the workers can like copy directly MATLAB objects. They need to work with MATLAB structures. Okay, so every time we get into an SPMD block, so a multi-parallel block, we need to work with MATLAB structures, not with MATLAB objects. So when the worker receives the MATLAB structure, then it can create a new MATLAB object. So, and now it has its own copy of the network. Okay, and here's where the worker calls process epoch to process its specific minibatch. So each of the workers is gonna compute a different minibatch for training and for validation. Okay, and once they finished, the first worker, or also called lab1, is gonna be in charge of saving the net. Okay, and sort of serializing everything. Then work outside the SPMD structure, the worker 1 is gonna save the net, is gonna load the net again, and it's gonna call accumulate stats. So all the workers have been working independently. They have been computing different minibatches, and now there is the need to like fuse or merge all those computations into one. So what is going to happen here is that we're going to take the derivatives compute by all these workers, and we are going to average them to come up with a like common advanced direction, and that direction is going to use to update the network, the parameters of the networks, like all together. The final result here is sort of equivalent to have run the network through like 5 or 6 minibatches, but this operation has been done in parallel with different workers doing different operations independently, something which is quite convenient. Okay, and then finally the statistics for training and validation are like accumulated also here, and we just clear the temporal variables. If we are not in evaluation mode, so we are in training mode, we save the states, so we save all the partial things we have, and finally we have some plotting functionalities that create the figures we usually see with the logarithm scale and the linear scale for the stats we have defined in our network. So in this case, like error and objective. Okay, and for both training and validation. And finally, we save a PDF with this plot. Okay, now it's time to have a look to the process epoch, which is where all the functionality happens. In any case, I will recommend you to play with this code we have seen so far, to try to understand how this piece of code is plotting the output of those specific layers name we have defined, and how you can change that. Going now to process epoch. This code is not too complex, but it has a couple of tricks. So the first thing we see is initialization of the momentum. So hopefully we have already seen in the short theory session that momentum is basically a way of including some sort of inertia into the optimization of our parameters. And this is how we sort of escape from valleys and so on. Then we need to initialize one value of momentum per each of our parameters, so per each of our weights, and those weights are usually coming from convolutions, so filters and biases. But it could also happen that we end up with weights in other layers, like for example in batch normalization or in any other layer you could define in the future. So in this case, any of those weights might be complemented by this momentum thing. Okay, then here again we have to take into account the possibility of having multiple GPUs, or not even one GPU. So in case we have one GPU or more, we need to move the network from CPU to GPU. This is very important. Okay, and the same thing have to be done to the data. So usually that's something that the get batch operation does, but otherwise we can do it here too. So yeah, in this case, every time we are creating a minibatch, in case the GPU option is set to true, we move the image destructor to GPU using GPU array command. Sometimes we also need to do that for the labels, especially when we are doing things like semantic segmentation, in which we have the loss function working at the level of pixels. So then it's very important to have the labels also on GPU. For these problems, not so critical. But usually we need to have all our data and network in the same device, so GPU or CPU. Then see how the momentum is also moved to GPU. Okay. In case we have more than one GPU, we need to initialize what we call the map of gradients. That's basically a MATLAB structure that is assigning different positions to. Is basically telling where each of the gradients is starting. So where is the gradient of layer 1 starting, where is the layer of gradient 2 starting, and so on and so on. here we create a subset according to the current mode. That could be training or validation, so evaluation of training. And this is the main loop. So we're gonna run a set of mini batches here. So from 1 to the number of subset, the total number of mini batches of our dataset for training or for validation. And we retrieve the batch size. So that's based on the batch size we define and the number of elements of the subset. Just because we might not have like a number of images that is like so we might have not enough images for the last mini batch. So we need to take that case into account, that the last mini batch might be smaller than expected. Then there's something funny here. This is a small trick. So probably many of you are already familiar with the concept of mini batch, but I don't know how many of you are familiar with the concept of sub batches. So usually there are a lot of limitations when working in GPU. So we don't have enough memory for computing mini batches of that are large. So we end up like computing very small things. But there is a trick to simulate that we have a larger mini batch. This basically so we can set like small batches of 5 images or 10 images, and we can run many of those small batches. But every time we run each of these batches, instead of updating the parameters of the network, we wait, and we basically keep averaging the derivatives computed from each of these mini batches or sub batches as they are called here, until we like have run, I don't know, a couple of them, like 10 or 20 or 100, and then with the output derivative of those sub batches we update the network. So that's sort of equivalent to having run the network through a very large mini batch. And this is something similar to what happens when using like multiple GPUs. Here in the training code we can see that we define it the sub batches to be 1. So we don't want the sub batch things to happen, but we could change this to a different number, and I actually recommend you to do it for fun. In any case, so here we have an inner loop like going through the sub batches in case we have any, but at least we're gonna have one, so this loop is gonna be run at least once. Well, basically this is just defining the starting point of the mini batch and the ending point according to the current lab in case we're using GPUs. Otherwise lab is going to be 1. Okay, the number of labs is going to be 1, so at the end it's going to be T, and the same for the end. So basically that's just operating with indices in order to get the beginning and the end of the batch according to the current iteration and the current sub batch. This is quite easy to understand if you just like spend 10 or 15 minutes of your time. Okay, if we don't have enough elements in the batch, we just skip this iteration. Otherwise, batch is gonna contain like the indices of the images, so image 100 and 300 because they have been like permutated, and with those numbers we call the getBatch functions we have defined. In this case, that function is defined here in our code. Okay, it's this one we have provided. It's expecting a couple of indices, and it's gonna retrieve the images and the labels associated to those indices. Okay, so the getBatch function is called with the current IMDb and the set of random indices we have chosen right now. In case the prefetch option is activated, we can already start like computing the beginning and the end of the batches and call getBatch like in parallel. This is useful, for example, when we don't have all the data set in memory. We are loading it from disk step by step. So once that we have like load the current minibatch, we can start loading the next minibatch, so we can save some time accessing disk and so on. But well, this is not the case here, since we have all the data set in memory. So the option of prefetching is switched off. Okay, so if we are in training mode, we set net mode equal to normal. Otherwise, we set the mode equal to test. Remember that different modes make things behave in a different way. For example, the dropout behaves in a different way, batch normalization behaves in a different way, and so on and so on. If we were using Minibatches, sub-batches, probably, and we need to accumulate the derivatives. Okay. So that's the meaning. If S was different from 1, so if the number of sub-batches was different from 1, so we have to switch on the accumulation of the derivatives. That means that in the first pass of this loop, this is going to be switched to, this is going to be activated, and then every time the network is evaluating in the backward mode, the derivatives of the different layers are going to be accumulated here. Since this is not the case, and the number of sub-batches is equal to 1, this field is going to be set to false, and we are not going to be accumulating derivatives. Okay, here is where the evaluation of the network happens for the current minibatch. Okay, we have to provide with some derivatives because we're going to perform at the same time forward and backward propagation in the same code. Okay, first forward propagation, then backward propagation, as we saw before in the evaluation code. So if computing derivative has some value, we keep going, otherwise we return. So if we keep going, we're going to run the second loop that is in charge of doing the backward propagation and compute the derivatives and assign all the derivatives. Good. If we are in test mode, as we said before, we just call the evaluation code with the input. We don't need to assign any derivatives and so on. Just the forward propagation is gonna happen. Okay. So up to this point, if we are in the training mode, we have already computed the derivatives that we need to update the network. This has been done due to the magic of back propagation, and now we have them. We can start like optimizing the network itself, adjusting the parameters. Okay, here some of the statistics are extracted from the network. We can see that function later, but the important part happens here in accumulate gradients. Accumulate gradients is on charge of performing the optimization of the network itself, so it's the one on charge of adjusting all the weights. So in case of the mmap structure wasn't empty, remember that that's an structure we built before for the multi-GPU case. So here we have a barrier. Here we have a barrier. So all the labs are gonna be stopped here, but before that they are gonna write their gradients from the network to the map. So this is a serialization point. At some point, so during the evaluation of this loop, when we have several GPUs, each of the labs, each of the workers is gonna be working independently in its own version of the network, and it's gonna be writing the gradients and the derivatives on each version of the network. So at some point, and that point is here, we need to write those different gradients into a common structure, okay? And that common structure is mmap. And then we wait until all of them have performed this operation. Then accumulate gradient is gonna take that structure in, and it's gonna combine all the gradients and perform the optimization of the network according to that. If mmap hasn't been defined because we are not using multiple GPUs, then the code is just gonna ignore that and perform like the optimization in the traditional way without accumulation of the gradients. So let's gonna have a look to accumulate gradients. So the end of this code is just to print the statistic we have computed already. So then the number of minibatches, this is minibatch 1, and minibatch 1 consisting of this number of images, and these are the statistics, and so on and so on. So you can have a look to this by yourself. And yeah, at the end we reset the net in order to like delete intermediate results, and we move back the net to work to CPU in case we were in GPU, just to be able to save the net to disk, because every time you want to save something to disk, you have to move it from GPU to CPU in case you have it in GPU. So okay, accumulate gradients. This is where the update of the network happens. So this piece of code is the one in charge of doing the merging of all the gradients in case we have like multiple GPUs and multiple workers. So basically it takes into account the number of GPUs, okay, initialize a temporal structure that has the same size as the parameters of the network. So there is a loop here for each of the layers, well, per each of the parameters. So all the layers which actually have parameters like convolution, batch normalization, and so on, okay, and it creates this temporal structure with the size of the current parameters. So for example, the current convolution, and basically so since we are gonna be in a specific worker right now, in a specific lab, we already have like the output of our derivatives for the lab. We just need to compute the output for the remaining labs. So that means like for all the GPUs we have, we take the difference between, like, for example, 1, 2, 3, 4, 5 and the current lab, which is for example 1. So we're gonna just go through like the remaining labs 2, 3, 4 and 5. I hope this is sort of clear. So if we are in lab 1 and there are 6 labs, we're gonna take the remaining derivatives from 2, 3, 4 and 5. So all the labs that are not the current lab, all the workers that are not the current worker. So basically we're gonna keep like accessing nmap data G. So G is the one of the labs, one of the workers, that this is not the current worker, and we're gonna keep like adding the parameters of the network to the temporary structure. So we are accumulating the parameters. And then we use the temporary structure to combine it with the current derivatives. So that's the derivative computed by the current lab, for example lab 1 in this case, and we leave it in the derivative field of the current lab. So basically this means that there is a sort of master lab right now, and we're gonna use its network structure, okay, and the remaining labs have stored the information in the mmap data structure. we retrieve the information of the derivatives stored in that structure, we accumulate it in a temporary variable, and at the end we add it to the derivatives of the current network of this lab, and that's it. In case we only have one lab, so nothing of this is gonna happen. So yeah, at the end what we have is the net params p dot there, so the derivatives of the current parameters that have been computed before, and that's it. So now this is new for this switch here is new for version 17. Okay, so there are different ways of doing the update. So for example, we can define a specific training method for each of the layers. That means you might end up training convolution 1 and 2 with one method, and batch normalizations with a different method. This is actually done for the sake of batch normalization layers. Usually the traditional way until this version was to use this piece of code here. This piece of code represents a stochastic gradient descent. So this is an stochastic gradient descent update that incorporates weight decay as a regularization method and momentum in order to escape from valleys, in order to escape from planes, planar regions. So the update equation is like the one defined in the theory. So the only thing we need to take into account is that usually, for example, for the weight decay, there is a global weight decay variable you can define in options. So this is something we did here, I believe. Yeah, weight decay 3 to the 10, 3 by 10 to the powers minus 4. Okay, and that global option is going to be combined by a local weight decay defined in the current layer. So the effective weight decay is going to be the combination of the weight decay of the current layer, the parameters we are like studying, the global weight decay. And the same happens for the learning rate. So we have a global learning rate, so the learning rate for the current epoch, and that's going to be multiplied by the local learning rate of these parameters. For example, for convolutions, you might have two local learning rates, one for the filters and one for the bias, and they can be different. So since the filters and the bias are stored as different parameters, so they are going to be different p's here, so we will end up like performing two different ways of adjusting these two fields. Then the same for momentum, so each of the parameters can have a different factor for momentum, plus the global momentum, and the effective momentum is the combination of both. And well, this is the update already, so this is the combination of the momentum and the weight decay and so on with the current derivatives. So as expected, the update using stochastic gradient descent has into account the current derivative of those parameters, the previous value of those parameters, okay, and also the learning rate and the momentum, and basically that's combined to produce the new values. In order to really understand this, it's much easier to have a look to the equations defined theory. This is basically a compact way of mixing learning rates, wave decays, and momentum. But if we like reorder or rewrite this equation like step by step. At the end, the only thing happening is that we evaluate the function, we compute the loss, the derivative of the loss, having into account a penalizer done by the weight decay, which is the L2 norm of the weights, so of the current parameters. We compute the average of the weights to have the momentum, and we incorporate those things into the gradient descent update, which is basically then that the new weights are gonna be the previous weights minus some learning rates multiplied by the derivatives. So in this case, instead of having the derivatives of that parameter directly, we have this combination coming from applying momentum. So we combine derivatives like as a historic of derivatives, and for doing that combination of this history of derivatives, we also need to take into account the previous learning rates and weight decay and so on. But in general, the equation is quite simple. It's basically a simple gradient descent update. Okay, and this is the classical method for updating parameters. But have a look here. We also have this case called average, and this is mainly for batch normalization as it's specified here. So the thing is that batch normalization is a layer we haven't studied yet, but what it does is a sort of like normalization of the data. So basically, given a multi-array X, that array is normalized by removing its mean and dividing it by its standard deviation. Afterwards, with that normalized data, the batch normalization applies like a shifting factor and also a scaling factor. So the normalized data is shifted and rescaled, and the shift and the scale are learned during training. So those are the three parameters of the batch normalization. Then the problem of that layer is that although it's very useful for training because it's sort of regularizing all the gradients and making the things to converge faster, during validation its behavior is stochastic, because when we perform the mean subtraction and we divide it by the standard deviation, the mean and the standard deviation are computed from the current images of the current minibatch. That means that if you are evaluating one image, the result of that image is gonna depend on the remaining images of that minibatch. So having different orders or different images in your minibatch is gonna change the results, and this is a behavior we want to avoid. Usually for that, what people do is to compute a sort of global statistics. So in order to have like a global mean and a global standard deviation, having into account all the mini batches of your training set, and then during validation, instead of computing the mean and the standard deviation of the current mini batch, they use those global mean and global standard deviation fixed. So the batch normalization doesn't depend anymore on the current images, but on those global statistics that are fixed. But in order to do that, the training mechanism gets quite more complicated. Okay, and it seems to be simpler and cleaner, instead of computing those statistics, so the global mean and the global standard deviation, to learn them. So basically this is what this guy is doing, is trying to learn the global statistics, which are the best statistics that can be used in order to fix those in validation. Okay, without computing the actual statistics. And in order to do that, the learning rate is fixed. So as you can check here, it's just using the local learning rate of the layer. In this case, this is probably going to be a batch normalization layer. So that means that if you define a variable learning rate as your global learning rate here, that is something that is decreasing for different epochs, that's not gonna produce any effect here, because this guy is gonna be based only on the local learning rate that you define for a given layer. So in this case, that would be this thing, like when we perform the initialization and we define a learning rate for a given layer. Okay, and then it's gonna use that learning rate to update the values using the derivatives of that field. That is gonna be like the moment field, which is one of the parameters of the batch normalization layer, as we will see later in an upcoming session. But you can see here that there is no weight decay, there is no momentum, there is no anything. So this is a very simple mechanism to keep adjusting slowly the global statistics in order to be used later for batch normalization. But this is quite cool, not only because this average method, but also because now you can define that each of your parameters, each of your layers, is gonna be like optimized or adjusted in a different way. So you can have like L2 decay for convolution filters, L1 decay for biases, you can have this thing for batch normalization, and many other things for other layers. So you can start doing very sophisticated training with this code. Okay, so I think that this is so far everything I wanted to explain about the training code, and I recommend you to play with it for a while in order to really understand what's going on, so we can perform some like debug using MATLAB to run the code step by step and see what's happening here.